Does this football look right to you? A little deflated? In 2015, an NFL team was accused of underinflating footballs to give their team an unfair advantage. The NFL even launched an investigation. Turns out, the chemistry principles that you will learn in this unit played a major role in their findings. Gas laws are important for more than controversial football practices, and it's a good place for us to start. This is Real Chem. The rules said that the footballs had to have a pressure of at least 12.5 pounds per square inch. So they were set to a minimum pressure at room temperature, let's say 77 degrees Fahrenheit in the locker room. But then the game was played in January in the Northeast. The temperature was likely below freezing. As the temperature falls, the average speed of the molecules decreases. The molecules inside the football hit the skin of the football with less kinetic energy, and the pressure goes down. Even though the number of molecules in the football didn't change, the pressure likely fell to something like 11.5 psi. Cheating? Depends on how much the gas laws the team was familiar with, I guess. You decide. So here's the question. Why is the number of molecules even relevant, rather than the type of molecules? Would it have changed things if they had inflated the ball with a different gas? Well, amazingly, the pressure of a gas to a good approximation doesn't depend on the types of molecules in the gas. The good approximation I'm referring to is the ideal gas law, and it works surprisingly well. Well enough that it applies to a gas in a football. The mass of a nitrogen molecule is about 7 times that of a helium molecule. It's like the difference between a Mini Cooper and a semi-truck. Yet, if I fill a football with a few billion nitrogen molecules, and another football with the same amount of helium molecules, and assume the volume and temperature of the footballs are exactly the same, the pressures would be the same in both balls. As surprising as this is, it also has some pretty amazing consequences. For example, these footballs may have the same number of gas molecules in them, but because a helium atom is 7 times lighter than a nitrogen molecule, the gas in the helium football is 7 times lighter than the gas in this nitrogen football. Now, most of the mass in the football is in the skin, not the gas, so it isn't that noticeable. But fill a blimp with helium, and the low mass allows it to float over the stadium on game days, giving us those awesome overhead camera shots. Increase the mass of the filler gas a bit, using, say, nitrogen molecules, and the blimp stays on the ground. Understanding gas laws is essential for this unit. It starts by looking at the fundamentals of gas laws and applying them in context. We then apply them to stoichiometry to understand how we predict and control reactions between gases. The unit ends by looking at kinetic theory with relation to gas laws, molecular velocities, diffusion, and the exceptions to ideal gas behavior. By the end of this unit, you'll be able to fill a football just right. Now let's get to work. This is Real Chem.